Hello and welcome back to Global Climate Change. This is Lecture 8. This week I would like you guys to read Chapter 4, pages 19 to 29, as well as Chapter 11, pages 21 to 24. So let's get started. So first today actually we're going to talk about radiative forcing. That's pretty much the complete thing that we'll talk about. There's a couple things that come into radiative forcing that we'll talk about that is related to it, but this whole lecture is pretty much radiative forcing. So what is it? It's a value to quantitatively determine a forcing's effect on the climate. So the greater the magnitude of the value, the larger the warming or cooling effect. So you're basically putting a number on how much a single thing is actually going to affect our climate. And once you put a number on it, you can say, okay, well, the larger the number, the greater the warming or the cooling, and the smaller the number, the lesser the warming or the cooling. And now positive values do indicate warming and negative values indicate cooling. You think of like a number line, right? The further towards the ends is going to be the greater amount that it's going to take effect, and closer towards zero is actually where, there'll be less effect. Now, some forcing factors have a warming effect. Now, some examples of that would be increasing in greenhouse gas concentration, increases in sunspot activity. We went over these, so we do know that it has a warming effect on our climate. And others also have a cooling effect, like aerosols, stratospheric ozone, or I don't know why decreases in there. um, Okay, so the ozone layer, like speaking of the ozone layer, right? It absorbs ultraviolet radiation with greater efficiency in the upper region. Okay, so basically, right here is where our ozone layer is going to be. Right here is where it's going to absorb ultraviolet radiation. As we know, we've learned this before. This is good. It blocks out harmful UV rays from us. And this is in the stratosphere. Okay. Oh, and when it's absorbing that UV radiation, it does actually have more warming in the stratosphere. But we're experiencing stratospheric cooling. While the troposphere is warming over time, obviously global warming, right? The stratosphere may actually be cooling. The reason why is because the ozone layer is depleting. We all know about the ozone hole. We've heard of the ozone hole, hopefully. Which basically is, the fact that over time the amount of ozone in the stratosphere has decreased. Okay, and this is actually due to increases in chlorofluorocarbons, which would be CFCs. Now, what are CFCs? They're chemicals that contain carbon, chlorine, hydrogen, and fluorine. Okay, the chlorine actually breaks that O3 molecule into one molecule of oxygen and two molecules of oxygen. So just a singular O and then O2, because O3 is actually what ozone is. Now, CFCs originate from refrigerants, aerosol sprays, cleaning solvents, and bubbles and foams. This is what's led to like a ton of different regulations on how they, dispose of refrigerants, freon in your vehicle, things like that. Also, aerosol sprays. Now, the depletion of ozone became an important topic in the 1970s and the 1980s. So I am actually old enough to remember, or maybe had, this big thing. My dad actually, he called it like a bird's nest on top of my head because, I'd tease my bangs and put them up and they'd use this aqua net, and just spray the heck out of it. And it would just be like this like solid mass of hair on top of your head. This is really popular during the 80s. So basically, the aerosols in that hairspray actually, included CFCs, and they actually did away with that. And then you can't really get hairspray now the way that it was back then. Thank God, because we probably had pretty bad hair. But, so that's when I think of CFCs, I immediately think of, 80s hair, I guess. But, it wasn't more than just hairspray. But, that is one of the things, propellants and aerosols, that you found it. Here's actually like some graphing here that kind of shows you, here's the ozone hole, how it's changed over time. It kind of peaked here in 1994, 96, and started going down again. But this hole basically is not going to absorb that UV radiation. And because it's not absorbing that UV radiation, we're actually going to experience cooling in the stratosphere. Okay, and why is it actually over Antarctica though? If you notice, here it is at the pole is where this hole is. Okay, it's because chlorine breaks up CFCs more easily at colder temperatures. Okay, the presence of polar stratospheric clouds helps speed up the chemical reactions that remove chlorine from the CFCs. One reason the stratosphere may cool is due to a decrease in ozone concentration. This is what we were just talking about, right? Without the ozone, actually absorbing those UV rays, there's going to be actually cooling going on. Another is due to an increase in anthropogenic greenhouse gases. As CO2, CH4, N2O, and other greenhouse gas concentrations go up, less outgoing. Sorry, I couldn't quite hear you. I'm not sure what Siri thought there, but so aerosols, microscopic solid or liquid particles. This is what they are: aerosols. So, what are aerosols? They're microscopic solid or liquid particles suspended in the atmosphere, ranging in size from about 0.01 to 10 micrometers. So, these are very, very, very small little particles that you find in the atmosphere. Obviously, that's what keeps them suspended up there, otherwise, gravity would cause them to fall. Now, they can act as CCN. Meaning of that is, cloud condensation nuclei. That's going to be the thing that's going to allow that the water vapor to condense, onto it and create a cloud droplet. But they also alter the Earth's radiation budget through the direct and indirect effects. Okay, so short atmospheric lifetime, on the order of days to a couple of weeks, in the troposphere. So they're not really up there for very long. Okay. But they can stay up there then go back into the ground or ocean. Okay, so examples are going to be dust, smoke, okay, from sulfate, black carbon, or organic carbon, or salt. One of my professors actually from undergrad, he actually was in Oklahoma. He went to Oklahoma State during the big tornado. I think it was 1999. I could be remembering the wrong date, but anyway, this big tornado went through, and it's crazy because he said after the tornado went through, well, you guys might know this, but the dirt actually in Oklahoma is red. It's like kind of a rusty color. So anyway, it brought so much of that dirt and dust up into the atmosphere that the sky actually appeared to be red for a couple days, and it took a couple days for that, that dust and that I say like the dirt basically to come out of the sky, fall down to the ground. So dust definitely, dirt can just get up into the atmosphere through various different ways. Haboobs also will do that down in the south, which are like dust storms that they have. Down Vegas has them. My son lives down there, and he always tells me when they have one that go through. Okay, so here's like kind of a picture, of what it can look like when it's in the air. Here's another one. Okay, so usually in our atmosphere we see pollution as large clusters of aerosols. So when you go down to LA, I went up there actually to the Hollywood sign, and you can really kind of see that pollution down in LA. When you see it from afar, humans can't see greenhouse gases, but we can see the effect of pollution. And the reason why is it can reflect shortwave radiation, but it can also absorb shortwave radiation. It depends because it depends on the type of aerosol that we're looking at. It could also absorb long-wave radiation. In general, the net effect of aerosols on the energy budget is to actually cool it, okay? But it can warm it. Some of them warm it, some of it cool it. It kind of depends on what we're looking at. Okay, so you can see how, here's some aerosols here, okay? Some of these aerosols are actually absorbing the incoming radiation. Some of it is scattering it. So, but the net effect is actually cooling. You can see that the energy coming in is generally going to be reflected out. As a result of human activities, they have increased in concentration since the mid 1800s. So, driving our cars and, deforestation and, manufacturing, lots of different things that we actually do, just, a byproduct of what we do is, aerosols. So two indirect effects. First of them is going to be increasing the anthropogenic aerosols to cause a decrease in droplet size, resulting in a brighter cloud. So there's going to be a higher albedo. Basically, the takeaway to this is going to be, a higher albedo. This is going to actually have a cooling effect, right? Because it's going to reflect more of that incoming radiation. And the radiative forcing is going to be negative because it's not going to have, warming. It'll have a cooling effect. The secondary effect is going to be reduced cloud droplet sizes, causing a decrease in precipitation. Okay, so there's going to be a longer lasting cloud as well as a thicker cloud. Now, the natural sources are going to include of aerosols, because there is natural sources, which is going to be dust, salt, and smoke from volcanic eruptions. But there's also anthropogenic sources, and those are going to be things like factories, cars, power plants, deforestation. I kind of just went over those. Aerosol observations from NASA satellite. You can kind of see here off of, what is that, San Diego, Baja California here. You can see that there's definitely an increase. Right, here's our index. So up here in the reds is going to be a higher amount of aerosols. So, right here, we're going to see quite a bit. What is this? Does it give a date? October 26th of 2003. There was a high amount of aerosols right here off the west coast. You can see, there's fires around here, so you guys are well aware that, fires actually will put aerosols into the atmosphere, and that's, what blocks the sun. That's also what can make, the sun look different, like it'll look kind of yellow. The atmosphere, like if you look out in the air, it kind of looks yellow. It's because it's scattering more of those yellow, preferentially, wavelengths of the light instead of the blue. See how this kind of gives you like a yellow kind of look? Like it has a filter kind of over it. And here is, Asia. There's a lot of manufacturing over there, so there'll be a lot of aerosols, due to that, a lot of pollution. So you can kind of see over here how there's quite a bit of dust. Actually, this is going to be dust, but there is also aerosols due to that as well. Smoke from biomass burning, things like that. Now, sulfate aerosols is kind of like a subcategory of aerosols, and its natural source is going to be volcanoes. But there's also going to be an anthropogenic source, which would be burning of fossil fuels, hydrocarbons, such as coal and oil. That's going to be like the coal-powered power plants, and also, our vehicles coming out of the tailpipe. The overwhelming around 90% of sulfide aerosols are anthropogenic. So by far, we're going to have more being from human-induced causes. Example is going to be SO2 released during coal combustion, which is, like I said, during the coal burning power plants. And these are going to act to reflect incoming solar radiation. So the actual total effect on Earth's energy budget is going to be cooling. So hopefully by now you're thinking that the radiative forcing would be negative. There's also going to be black carbon aerosols. The natural source of this is going to be like biomass burning, such as forest fires. When I worked at NASA, and I think I told you guys I was actually looking to identify specific cloud types off the coast of Africa. The reason why they were so looking at these specific clouds, and they were flying all of these, planes actually through these clouds and through the specific area, is because there's a bunch of forest fires actually happen over in Africa. And the winds kind of bring those aerosols over that specific area. So we were able to not only look at the clouds, but also look at the aerosols and the interactions between the two. So there's also anthropogenic sources, which is incomplete combustion from coal and diesel engines, human-induced biomass burning, deforestation. These are all going to be, ways that it'll actually get into our atmosphere, not naturally. And this is also known as elemental carbon or soot. I know it actually soot. I used to have a fireplace, so you'd see the soot on the back. It's definitely potentially harmful if inhaled. It absorbs solar radiation. Like I said, I used to have a fireplace. The soot would be kind of in the back of, I maybe think of Mary Poppins, right? And they cleaned out the fireplace there. It's black, it's really dark in color. So it has a very low albedo, which would have a warming effect because it absorbs that solar radiation, okay? Which hopefully by now you're thinking radiative forcing would be positive. Okay, so then we also have organic carbon aerosols. The natural source of that is going to be biomass burning, okay? And the anthropogenic is going to be fossil fuel burning as well as deforestation. Now, these aerosols aren't absorbed they don't absorb the solar radiation, they actually reflect it. Okay, so total effect on the Earth's energy budget is going to be cooling, right? It reflects it, okay, which would be negative radiative forcing. Now, we have other aerosols like sea salt, which comes from the ocean. Those are highly reflective, okay, which would have a cooling effect or negative radiative forcing. Another one would be dust, like I was telling you about that, like how that tornado brought them up there. Those come from natural, like soil, volcanic eruptions. Anthropogenic sources would be like homes and offices. We're not really sure exactly the effect on the Earth's energy budget. Now we get back to radiative forcing here, okay? Remember, radiative forcing is a change imposed upon the climate system, which modifies the Earth's energy radiative balance. Now, this is usually given in units of watts per meter squared. Here's kind of a nice little depiction of that, right? So this is reflected solar radiation. It's going to have 102 watts per meter squared, right? They're reflected by clouds, aerosols in the atmosphere. This is incoming solar radiation. 161 of that is going to be actually absorbed by the surface, but 23 of them will be reflected off of the surface, right? So then we're also going to have, starting at the bottom here, this is incoming. So coming outgoing is going to be surface radiation, being 396, and then 356 of that is going to be absorbed by the atmosphere and clouds, with 30%, also emitted, and then, emitted by the atmosphere is 169. All of this total together is going to be outgoing long wave radiation of 239. We also have, incoming here with back radiation from atmosphere and clouds, and then outgoing, which would be like thermals, right? So we have all these different things in our radiation budget, right? But the different things that are forcing, meaning these are different things that either like warm us or cool us in one tendency or another, and they actually all work towards our radiation budget. Changes in individual forcings produce changes to the Earth's energy budget, like I just said. The magnitude of the radiative forcing determines how strong the effect is. So if we look at this, right, this is going to be stronger, 300, actually, I'll look at this here. Okay, so this is 341 versus 333. So we know, the incoming solar radiation, 341, is obviously going to be stronger than the back radiation from atmosphere and clouds. Now, radiative forcing is computed by comparing pre-industrial energy balances from 1750 with today's energy balance. I realize that this is a while ago, but for 2000. Greenhouse gas concentrations have greatly increased over the last 150 years, which is going to cause positive radiative forcing. Now, remember we were talking about the ozone to begin with. This exists in the upper atmosphere. The stratospheric ozone levels have been declining from 1970 to 2010, and this is going to cause radiative forcing of negative. Okay, this exists in the lower atmosphere. The tropospheric ozone can mix with fog and or haze to produce smog. Okay, remember, so good in the upper atmosphere, but bad in the lower atmosphere. Okay, tropospheric ozone, these levels have increased over the last 50 years. So, stratospheric ozone is declining, where tropospheric ozone has been increasing, which also has a positive radiative forcing effect. Now, another thing that actually can contribute to a change in radiative forcing is going to be changes in land use, which have contributed to albedo changes. Like deforestation has been one of the largest contributors, and the highest latitudes have been the most affected. Okay, so pre-industrial snow-covered forests, right, are going to have a lower albedo, but the current open snow-covered areas would have a higher albedo. Now, large uncertainties exist in details of the changes. So, this is another thing that we're a little bit uncertain on, but a lot of studying has been being done currently in these areas. This is actually going to have a negative radiative forcing effect overall. Now, this is kind of a graph that we look at to look at the radiative forcing, components. This is going to be zero radiative forcing, where, remember I said like a number line, we're getting closer to, like the larger numbers on the positive are going to be having a larger warming effect. We're getting closer to the negative numbers, and like the negative would have a cooling effect. So we can see the total aerosol cloud albedo effect has the largest cooling effect in radiative forcing, but the CO2 are going to have the largest warming effect, actually. And then if we look at the total anthropogenic, by far we have warming, because we have the halocarbons here, the stratospheric ozone. There's a little bit of stratospheric, which most of the tropospheric is actually acting to warm us. Just different, like black carbon on snow is going to have a little bit of warming, but, land use will have more cooling. Solar radiance would have warming effect as well. So we really want to make sure that we understand here that CO2 by far has the largest radiative effect, and that the net radiative effect here is going to be, warming for sure. And that's all I have for you guys for this week. So I hope that you guys have a wonderful week, and thanks for watching.